Right, good morning, everyone. As usual, how did the homework go? And you have any questions about the homework? Please start putting them on chat. Okay. No questions? Kiana? Yeah? Anybody else? Okay, so we start with Kiana's question, and then if anybody has any other questions from the homework, please put them. So I look at 51. And here we are. 51. So we have to evaluate the following definite integral now, 0 to pi over 2 of sine squared theta cosine theta d theta. Okay, so first so basically we have to find the antiderivative. I mean, that's really what it is. So if we look at it, whenever we have the sine square, I usually put it sine theta to the power 2 to help us really see it. Okay. All right. So now that I did that, now I'm back to you. We're gonna do this. Okay. We're gonna do this, but I need your help. So we're gonna do it also two ways. First approach, we do not change the limit at the beginning. So you understand clearly this. Second approach, we're gonna change the limit at the beginning. So in the first approach, we basically only find the antiderivative. And then the second approach, we do the substitution and change limit at the beginning. So first, this one. I only want to find the antiderivative. What's the u quickly? Please, I want your participation to answer every questions you have. What?
Sine theta.
Sine theta immediately. Because we see the u, we see its derivative, just really actually staring at us. So my du is to cosine theta d theta. And this is a problem where the substitution is, that is actually very clear. That's the u square. And this is the du. So it's 1 over 3 u to the power 3. I didn't change any limit. I have to go back to my original variable. But this is only the antiderivative. Now I want to go back to my definite integral. So equal. We evaluate this between 0 and pi over 2. I did not change the limit. I have to express everything in terms of theta again. So the rest is evaluate at the upper minus at the lower. So I will have a third, but here I'm going to give a remark. This third actually could be factored out at the beginning for the following reason. Suppose I keep the third here. Minus a third here. Then realize that this third and this third, I could have factored it out at the beginning. And sometimes it makes the problem a little bit easier. So because I have a third when I'm computing the antiderivative at the upper, and I have the third when I compute the antiderivative at the lower, because of that, I can actually start by kind of pulling the third out times the whole thing. The only reason we do it, we can do that, you don't have to, just to make the math a bit simpler. So finally, I will get a third. This is a 1 minus 0 equal a third. End of the problem. Now the second approach, which is basically the same thing, but the only difference is that I change my limit at the beginning, and then I don't go back to theta. I keep my integral in u. So I will do it also just so you have comfort in doing both of them. Okay, so the second approach goes like this. The principle is the same. I need the antiderivative. The only thing I'm going to do is change the limit at the beginning. So I'm going to do the same thing. U equal sine theta. Du cosine theta d theta. The only change is here. The only change is right there. I'm going to change the limit here. If theta is, that's the lower limit, is 0, then my u is the sine of 0, which is 0. That's for theta. Now, for theta equal pi over 2, my u is the sine of pi over 2, which is 1. And now I substitute, but also I substitute the limit. So that means that this is going to be equal to the 0 stays 0 because that's the sine. The pi over 2 go to 1. The sine square is the u square. The cosine is the u. Now, what happened is that this definite integral is equal to this definite integral in u. At this stage, I do not go back to theta. I have a new definite integral in u from 0 to 1. I don't go back, which is going to give me a third times 1, 0, which is equal to a third. Okay. All right, so now we look at the other question you guys asked, number 55. Number 55. And then I start the review, answer every questions you have. Okay, number 55, let's see what it is. Okay, integral from -1 to 2 of x square e to the x cube plus 1 dx. Okay. Now this one I'm gonna do it the second approach. It means I'm going to change the limit at the beginning, just for a change. All right. But basically, regardless how we do it, the bottom line is to find the antiderivative. And let's see how we're gonna find the antiderivative here. So what's gonna be my u? And of course my du.
X cubed plus 1.
X cubed plus 1. I mean, it's just barely staring at us. That's my u, and its derivative is clear. The derivative is here. The derivative of that is part of the integrand. It's the 3x squared. So up to a constant. That's always the way we have it. So my du is the 3x squared. I want to change limit immediately. And actually here we know that we have to divide by 3. Limit. X is -1. My new variable will be -1 to the power 3 plus 1, which is equal to 0. If my x is 2, my new variable is going to be 2 to the power 3 plus 1 is equal to 9. And now my integral here would be the integral of the lower limit. Now I change it, becomes 0. The upper limit is 9. Now I have x squared. I don't have x. So from here, I can deduce. Divide by 3, I need my x squared dx. So my x squared dx, this piece here, is a third du. And this is e to the u times a third du. Now, 1/3, I can pull it out, leaving me with that. And then I am actually done at this stage. I changed my limit, so I don't have to go back to x anymore. So it's a third. I'm listening.
How'd you get E4?
Because I did not get E4.
Oh, that's a U, okay.
Thank you. Okay.
All right, thank you.
No problem. So it's equal to that. So finally, I will have 1/3 e to the 9 minus 1. End of the problem. Okay. Okay, now you guys asking questions from the review. Let me see. Problem 7A from final exam review. Very good. I did not print the review, so I have to. So I will look at that. Number 7A. You have to give me 1 minute so I can have the review in front of me. 7A. Very good. So the question is, use implicit differentiation to find dy dx. Right. And it's x squared plus 1. All right. Okay, so I will do that because I'm sure that you guys have forgotten implicit differentiation. Okay, implicit differentiation is basically the idea is that I don't have y explicitly as a function of x. So I'm not giving you y as a function of x and tell you to find its derivative. I have an equation that relating x and y. And basically, I can, in a way, solve for y as a function of x, but it's very hard. So we don't solve for it, but we keep in our mind that it's not a y here, it's a function of x. So there is a certain function of x hanging in there that I don't know it exactly. So how do we proceed with implicit differentiation? We said that this is a function of x, and this is a function of x. So the derivative with respect to x of the first term is equal to the derivative with respect to x of x squared plus 1. Okay, and now I want to differentiate. So this here, I have a product of two functions. So we have to be very careful. I have a product. I need to use the product rule. So the product rule tells me it's the derivative of the first term. It's a 1 times the sine of xy. So I'm using the product rule plus the product rule plus x times the derivative with respect to x of sine xy. Product rule verbatim, which is equal to the derivative of x squared. This is 2x plus 0. Right. So now let us compute each term. So that's the sine of xy plus x times. What's the derivative of sine xy? Let's be very careful. This is x, and y is not y here. It's a function of x. As long as we keep this in mind, this would be easy. So it's like I have sine of an inside function here. So this is here. This is my inside function or my inner function. So what's going to be the derivative? It's the derivative of the outside, which is the derivative of sine, which is the cosine evaluated at the inside, times the derivative of the inside. Okay, I'm going to do it slowly, so we understand. Times the derivative of the inside. It means the derivative of xy, the derivative of that. I change from d dx to prime just to make it a bit easier. So now what's the derivative of xy? So times the derivative of that, derivative of the inside. Okay, one more step and we will get the derivative. Plus x cosine xy times. What's the derivative of the inside? That's again a product. So again, I need the product rule. So what does the product rule tells me? Derivative of x is 1 times y plus x. Y is not a y. Y is a function of x, but I don't know what it is. So I just keep it y prime. Okay, so that's the differentiation part. Now I need to solve for y prime. It means I need basically somehow to isolate y prime. So now we do the isolation part. So to isolate y prime, first I need to move this to the other side. So I'm going to have x cosine xy. So now it's algebra at this stage. Algebra, we have to do it carefully. This is equal to 2x minus the sine of xy. Okay. I need to remember, I need to isolate y prime. I can divide by x cosine x both sides. So I will have this equal to, actually you can, if you want it easier, you can distribute and then you can isolate. This would be, make the math a bit easier. So I'm going to distribute, I will get xy cosine xy plus x y prime times x cosine xy, I know it's x squared, it's 2x minus the sine of xy. I need y prime. I have to take away that, so I will get x squared y prime cosine xy equal to x minus the sine of xy minus xy cosine xy. And now the last step is isolate y prime. So I will get y prime equal to x minus the sine of xy minus xy cosine xy divided by x squared cosine xy. Okay, so it's actually, yes, absolutely. Y prime is dy dx. So dy dx is a notation for the derivative. And the reason for the notation of dy dx, because the derivative is nothing more than the limit of the change in y over basically the change in x, when the change in x becomes small. That's where the notation dy dx comes from. Okay, so y prime or dy dx. The reason I use y prime just to make the notation a bit easier to work with. All right. Okay, so that's a good review for implicit differentiation. Now you guys can go through the other problems and review them. Now I have questions, please, as we move on. Important, you ask me questions. All right, so let me look at the other two, and then let's see what the other two is. 5. I can't read that. 5 BC. I want on the final review. If you can give me the problem on the final review. Patrick, give me the problem on the final review so I don't have to pull up all of them. Okay. While Patrick figured this question out, so give me the question from the final review. Okay, I would like to 2021C. Okay, so we can go through that. 20. Okay, number 20. All right. So 20 is 20 part C or all of 20. Be very clear, Patrick. 20 is 4 parts. Okay, 20 part C. All right, so we have the following function. It's sine x plus cosine x on the interval 0 to pi. And the question is, find the critical point and classify as max, mean, or neither. Okay? All right. Critical point. Critical point are, let us remember critical point are. Critical point are basically those points where the derivative is 0 or those points where the derivative doesn't exist. Those are the critical points. They are critical because at those points, local max and local mean occur. So that's why they are important. They are extremely important because whenever you have a function, you want to know when this function is peaking. You want to know when it's lower value. So critical point are those points. These are the points where the function have a local max or a local mean in general. So whenever we have to find a critical point, we have to find, whenever we have to find local max, local mean, we have to find a critical point. And to find a critical point, it's exactly when the derivative is 0 or the derivative doesn't exist. In this problem, it's sine plus cosine, we always have the derivative. So we have to set f prime equal to 0 and solve for x. Okay. So we're going to compute f prime in this problem equal to derivative of sine is cosine. Derivative of cosine is sine. So we're going to set cosine x minus sine x equal to 0 and solve. So it's going to give me that sine x equal to cosine of x. I have to solve for x. If we look at it very carefully, this is going to give me tangent x equal to 1. Because if I divide by cosine, I will have sine over cosine, tangent x equal to 1. And I'm only interested in what's happening in the 0 to pi. Now, when is tangent x equal to 1? Tangent x equal to 1 when x equal pi over 4. And can anybody think of another value? The sine and cosine are equal. So if you are on the unit circle, when is the sine and cosine are equal? They are equal at pi over 4. And exactly, and they are equal right here because both of them are negative square root of 2 over 2. So at pi over 4, so that's the pi over 4. And here, this is the 5 pi over 4. This is where the tangent are equal. So and x equal 5 pi over 4. These are the only value I'm interested in because I am in the interval 0 to pi. Very good. Now, okay, these are the critical points. Now we have to classify them as local max, local mean. The way we classify them is we have to study the sign of f prime. So we want to know when is f prime positive, when is f prime negative. And I'm only interested in 0 to pi, only interested in 0 to pi. So this is my number line. I don't want everything. 0 and 2 pi are not included, but I have to put my critical point. So that's my pi over 4 and my 5 pi over 4. And now, so here I am using what I call the first derivative test. So I'm using the first derivative test. There are two tests. Okay, the first derivative test. The first derivative test means that you find the critical point, you find the sign of f prime, and then you will decide. All right, to find the set sign of f prime, we have to take test point. So we're going to do that here. And I'm going to take test point. So I need a point here, one here, and one here. Okay. All right, so this is my x. And remember, here should be f prime because I'm studying the sign of f prime. F prime, which is the cosine minus the sine. All right, so let's take some value. Between 0 and pi over 4, the easiest value we can think of, the easiest one, is pi over 6. Between pi over 4, 5 pi over 4, we have a lot of choices. So, I'm going to pick pi because it's easy. Between 5 pi over 4 to pi, my easier choice will be the 3 pi over 2. So I'm taking easy one. Now I have to evaluate everyone. What is f prime at pi over 6? It's the cosine of pi over 6 minus the sine. So the only one's going to be nasty is this one. Now the cosine of pi over 6, if it's the square root of 3 over 2, minus a half. Now, if you plug in your calculator, of course, no, you don't need that. That's the square root of 3 minus 1 over 2. That's definitely positive. That's the only thing I care about. It means that's positive. Pi. At pi, I have cosine pi minus the sine of pi. The cosine of pi is minus 1, minus 0, negative in here. So that's where the derivative is 0. And at 3 pi over 2, I plug in, it's the cosine of 3 pi over 2 minus the sine of 3 pi over 2. Now the cosine of 3 pi over 2, the cosine of 3 pi over 2 is a 0. The sine of 3 pi over 2 is a minus 1. That's positive. Okay, so this is the sine of f prime. Now I need to analyze, now those below. What does this tell me? If the derivative is positive, it means my function f increases up to 0. And then it decreases after that. So my function is increasing up to pi over 4. Then it is decreasing. So at pi over 4, I definitely have a local maximum. Now, at 5 over 4, it keeps decreasing. And then right here is going to start increasing. It means I have a local mean at 5 pi over 4. So f has local max at x equal pi over 4, and f has local mean at 5 pi over 4. Okay, so that's how we study the sign of, if we have a function, I need to find local max, local mean. First, I go after the derivative. It's the derivative that gives me the information, not the second derivative. It has nothing to do with local max, local mean, where they occur. You set the first derivative equal to 0. You solve for x. Once you do that, then we have two ways we do. We can find out whether it's max or mean. One way is what we call the first derivative test. You study the sign of f prime, exactly like we did. Once you study it, then you look at it. Okay, what is this telling me? It's telling me we increase, we decrease, we increase. So increase, decrease, it's a max. Decrease and increase, we have a minimum. Okay. Now, all right. Let's answer that. So now I have 21C. Is this your question, Patrick? Actually, before I move on, this actually is interesting because this is going to bring me back to exam 3. So I asked the following questions. A good point, good time to actually point this out. Then I go to the other questions. In exam number 3, I gave you the following. A certain function has for derivative and second derivative the following. So I did not give you the function on purpose because you didn't need it. But I told you, okay, I gave you the first derivative. So I gave you information. And the question, I actually wanted you to know which information you need. Okay, and I gave you the second derivative. Okay, so it is x plus 1 times 3x minus 1. And the question is, find the critical numbers of f, and for every critical number, determine if it's a max, a mean, or neither. Now, critical number of x, I don't need to set f double prime equal to 0 because I don't need this set f double prime equal to 0. I can use f double prime, I'll mention that later, but to find the critical point only occurs when the first derivative is 0. So I gave you more info maybe than I need, but I wanted you to be able to pick up what you actually need. And a lot of you messed it up. So critical number, only f prime equal to 0, not the second derivative. It means x minus 1, x plus 1 squared equal to 0, x equal to 1, x equal minus 1. So those are the critical point. I didn't need to give you f. I'm asking about the critical point. Now, for each critical number, determine if it's a local max, a local mean, or neither. Okay, so now I need to do the sign of f prime. I have minus 1, and I have 1. That's 0, and that's 0. So what's going to be the sign? So we're going to do it a little bit fast. I have to take a number less than minus 1, so I need my test point here. I take minus 2 from here. I take 0, and I take 2, and I evaluate. At minus 2, I will have minus 2 minus 2. This is always positive, as you realize. So this is not really affecting the sign of the derivative. That's really what's affecting the sign. If I plug in minus 2 here, I'm going to get a negative number. At 0, that's always positive. So I'm really kind of focusing here. I'm getting also negative. And at 2, I'm getting positive. Okay. So now what can we say? The function is decreasing. It's flattening here because the derivative is 0. So somehow it's decreasing and it keeps decreasing. It's just flattened here. It doesn't really do. So the derivative is 0. It means the slope is 0, but the function keeps decreasing. So it's like it's flattening. It's like the cubic root. And then it goes down and back up here. So here, x equal minus 1 is neither a max nor a mean, because there is no change of sign. The derivative is not going from positive to negative. The function is keeping decreasing. So minus 1 is neither x equal to 1 local minimum. Basically, end of the problem. You actually didn't even need the second derivative. Okay, I could have given you the problem without the second derivative and you should be able to finish it. But the question is, I want to see if you know how to use the info correctly. Okay, now a comment in order. An important comment in order. We can use what's called the second derivative test. So if I have a local max, a local mean, sorry, if I have critical point, the second derivative test tells me the following. You evaluate, you take the second derivative, and you evaluate it at the critical point. Okay, 1, for example. And you see what you get. So f double prime at 1. I'm going to plug in 1. So I'm done with the problem. That's kind of another approach. And let's see how it works. The second derivative. I plug in into here. Don't set f double prime equal to 0. I use those critical points and I plug them into the expression of the second derivative. It's going to give me 1 plus 1, which is a 2, times 3 times 2, which is a 6, minus 1, which is a 5. It's positive. What info does this give me? This is my second, this is 1. The derivative is 1. The second derivative is positive. It means it's concave up. That's what it means. If it's concave up, it means x equal to 1 is a local minimum. That's another way you can find out whether you have a local max or local mean. That's what the second derivative test tells you. Second derivative test tells you. You find the critical point first by finding f prime equal to 0. And then you plug in the critical point into the expression of the derivative and you see what you get. And here I got local mean, which is agree with my result, previous result. Now, if I compute f double prime at minus 1, and some did this and analyze it very beautifully, I will get, I would get minus 1 plus 1, it gets 0. If the second derivative gives me 0, it means the second derivative test failed. What do I mean by fail? Or usually it's inconclusive. Inconclusive means that the second derivative test here does not really give me the information I need. I have to back up in this situation. So some students use the second derivative, they cut local mean, then they find the second derivative -1, they realize there is no conclusion. Then in this case, they backed up to the first derivative test. And that's really we have to. So if the second derivative test gives me 0, I have to use the first derivative. If the second derivative doesn't give me 0, I can kind of stick to it. But basically in this problem, my main thing is that the critical numbers are when f prime is 0. These are the critical number, not f double prime. F double prime 0 give me the inflection. And then we study the sign of f prime and we proceed. Okay, so please go over this problem. A lot of you messed it up. All right, now let me see where I am there. I have 21, number C. And Chris 3A, from which problem? I don't know which problem you're talking about. I will look at 21C and then I'll proceed. 21C. 21C. I have the function f of x equal 1 over 1 minus x squared. And the question is a full fledged. Okay. All right. All right, so 21C, f of x equal 1 minus x squared. This is very much was like your exam 3. I want a whole study of the, I will talk about that, look. Okay, I will talk about that. So 1 over 1 minus x squared. First, horizontal asymptote. Okay, it's a good time to study, to remember that. So what are the horizontal asymptote? Horizontal asymptote are those, to find them is really boiling down to find the end behavior of the function. So for the horizontal asymptote, we have to study the limit as x goes to infinity of the function and the limit as x goes to minus infinity of the function. That's how to find the horizontal asymptote. So now what's the limit as x goes to plus infinity of 1 over 1 minus x squared? That's the horizontal asymptote. A lot of you again messed this up. When x goes to infinity, this goes to infinity. 1 over something very large is 0. It means y equal to 0, horizontal asymptote. Now here, when x goes to minus infinity, again, when x is very large, 1 over minus x squared is very large. 1 over something very large is also large. It means y equal to 0 is a horizontal asymptote. So horizontal asymptote is the end behavior, is the behavior of the function when x becomes very large. 2, vertical asymptote. Vertical asymptote occur when, for the value of x that makes the function goes to infinity. So the value of x that makes the function goes to infinity are those x's where usually the denominator equal to 0. So for the vertical asymptote, I'm going to equal to 0. It means x equal plus or minus 1. So 2 candidates for the vertical asymptote, x equal to 1, x equal minus 1. It means when I'm going to graph the function, what's going to happen? At x equal to 1, my function is going to basically blow up. And at x equal minus 1, the function is going to blow up. And at the same time, as x goes to plus infinity or minus infinity, my function is hanging here. That's really where my function is, over here. So it goes to 0. Now it's when we study everything else where I can start the graphic. So now domain of increase and decrease. Increase, decrease. Here I have to study f prime and the sign of f prime. So what is f prime of x? All right, I'm going to use the quotient rule. So f prime of x equal the derivative of the numerator, which is 0, minus the derivative of the denominator divided by denominator square. Okay, which is going to be equal to f prime is 2x over that. So please, if I'm doing any stupid mistake, you guys be aware because I'm trying to be as fast as I can. Okay, so this is going to be equal to. Now I need to study the sign of f prime. Intuitively, we should know what's happening. My denominator is always positive. It means my f prime is going to be positive when x is positive. That's intuitively what's happening. But let us study. Sign of f prime. All right. My derivative is 0. So sorry, before I study the sign, I have to set the derivative 0. F prime of x equal to 0. It means this is 0. Equal to 0. What does this mean? Numerator over denominator is 0. It means the numerator equal to 0. The numerator equal to 0. So if a over b is 0, the only way this can happen if my a is 0. So it means my x equal to 0. So this is at 0, my derivative is 0. Now, when you study the sign of f prime, you also have to put the value when the derivative does not exist. And that's at -1 at 1, because those will affect the sign. And then you take test point. I'm going to skip that because you should know how to do that. So test point, I take -2, minus a half, and 2. I plug them into the expression of the derivative. When I take test point, I'm going to realize that I'm going to get positive here. And I will take negative here. You guys make sure you take the test point.
I have a question.
What?
Did you choose, did you put -1 and 1 because there were vertical asymptotes?
Absolutely, yeah, because the derivative doesn't exist. So they are also critical point. If we
All
go
right.
back to the definition of the critical point, they were the point where the derivative is 0, mainly, and when the derivative doesn't exist. Okay.
All right, thank you.
Yeah, remember, okay, and they are important because they will affect the sign a lot of time. It means the sign, usually when we do the number line, we say that, okay, if a function is 0 at some point, so the function is 0 only, like, let us say here and here. So prior to that, it cannot take positive and negative values. It's either positive or negative. Otherwise, it have another 0. That's really the idea here. Another thing that affect the sign is when the function doesn't make sense. So if the function doesn't make sense at some point, it could go positive from, it could go positive from one place and negative from another. So there will be a change of sign here as well. So whenever we're studying the sign of f prime, of a double prime or anything, what we should put on the number line when it is 0 and also when it doesn't make sense. It's not defined. Otherwise, we will not have a complete picture. Answer your question?
Okay. Yes, thank you.
So now this is f prime. So now what can we say? Negative, decrease, decrease, increase, and increase. So now my function f is decreasing on the interval, -infinity, -1, and on the interval -1, 0. At -1, the function is not defined, period. F is increasing on 0, 1, or 1 plus infinity. At 1, the function is not defined. Very good. Now, the second derivative. Okay, so I need the first derivative to compute that. So what's the second derivative? So now concavity. Concavity. So concavity means we have to study the second derivative. So what's the second derivative? Equal to. All right. The derivative of the numerator, which is 2, times the denominator, minus the numerator times the derivative of the denominator is, so that's the chain rule. It's 2 times 1 minus x squared times the derivative of the inside, which is minus 2x. And the whole thing to this power. So it looks really messy, but let's see how we can make it not that messy. Equal to. Now remember, I have to make this equal to 0. So let's see what I will have. Minus minus, it's a plus here. 2 times 2 times 2, it's in 8. X times x, x cubed, times 1 minus x squared. No, x squared here, sorry. I was wondering. Very good. Now how I'm going to set this equal to 0 and solve. So remember, I need to set this equal to 0 and solve for x. So if I am doing this problem, I said, you know, this 1 minus x squared and 1 minus x squared, I can actually factor it out. And I can factor out this 2. So this is going to give me, I'm factoring out the 2. I'll factor out 1 minus x squared because solving is factoring. The more we can factor, the better it is. I will be left with 1 minus x squared in here plus 8, sorry, plus, since I factor out the 2, plus 4 x squared. Okay, so the reason I factored 1 minus x squared because I can, and I know I am solving. And whenever you solve, factoring is the way to go. So finally, I will have 2 times 1 plus 3x squared over 1 minus x squared to the power 3. Okay, so that's my second derivative. Now, we're going to set f double prime equal to 0. Okay, can this occur? Can this occur? Back to you.
Only the numerator can be 0, equal
Can
to
the
0.
numerator be 0?
Oh no, because there's square
Exactly. 1
x
plus
squared.
x squared equal to 0. It means 3x squared equal to minus 1. This cannot occur. So the denominator is never equal to 0. Very good, but I need the sign of f double prime. And now the denominator is going to play a role. So when I'm going to put the sign, because the denominator doesn't make sense here and doesn't make sense here, it's going to affect the sign of the second derivative. Because the denominator is not always positive. I have here to the power 3. The denominator could be positive and could be negative. My numerator, never 0, but my denominator can be positive and negative, so it's going to affect the whole picture. So I'm going to take the sign of f double prime, and I'm going to do it here. And I'm going to take minus 2, 0, and 2. And I'm going to plug in into the expression of the second derivative. So if I plug in minus 2 here, I'll have a positive here. I plug in minus 2, I will have 1 minus 4, minus 3 to the power 3. I'm going to get a negative number here. At 0, I'm getting a positive number here. And at 2, I'm getting a negative number here. So let me analyze it for you. Let me analyze it for you. What's happening for the second derivative? The numerator is always positive, but the denominator, because I have to the power 3, could be positive and could be negative, it depending on x. So I'm taking the sign of f double prime. I have to take when the denominator, does it make sense? When the function is defined, minus 1 and 1, because it's affecting the sign of the second derivative. So now I have concave down, concave up, concave down. So my function f is concave down for x less than minus 1 or x bigger than 1 is concave up. For x between -1 and 1. Okay. The last piece. Oh, time is up. Okay. The last piece in this problem is to sketch the graph. And you definitely have difficulty sketching graphs. So to sketch the graph, we're going to do the following. I have everything about f prime in front of me, everything about f double prime. Now, what do I have about f prime, if my memory is right? Both of them has issue at -1, 1. The f double prime, it's 0 in here. And it is positive, and it's negative. F double prime, it's negative, and it's positive, and here it doesn't mix, it's not defined, and it is negative. So I'll put them both. And then what info I have? Y equal to 0, horizontal asymptote, x equal 1, x equal -1, vertical asymptote. So I put all those info in front of me and I proceed. Very good. Here we are. The -1, 1. Those are my vertical asymptote. Okay, horizontal asymptote. It means I know when x goes to plus infinity. So this line here is a horizontal asymptote. So the x-axis is a horizontal asymptote. Very good. Now, step by step, up to -1. What's going on? Decreasing, decreasing, as concave down. So it's decreasing, going down, concave, and it is concave down. So it's the and when x goes to -infinity, it goes to -infinity, my function is close to 0. So it's decreasing, concave down. At -1, we have an asymptote. Now, between 0, -1 and 0, decreasing, it's decreasing, and it's concave up. It's decreasing, concave up, and at 0, we have a horizontal asymptote. Sorry, it's the derivative is 0. It means we have a critical point. Now, my original function was 1 over 1 minus x squared. At 0, it's 1. So this is 0. My function takes the value 1. But that's the function now. And how it's behaving? It's decreasing, concave up, all the way up to 0. And right here, I have my horizontal tangent. That's the only way up. Okay, now what's happening here? Between 0 and 1, it's increasing, concave up. Increasing, concave up. My function goes like that. I am done with this piece. Last piece. The function is increasing, but it's concave down. So my function is increasing, it's concave down. My function is going to switch like that. And this is the asymptote. Okay, so that will be the graph of my function. Okay. Do we have a quiz? All right. Now, here is the thing, how we're going to proceed. You will have a quiz on Friday. That's definitely. Tomorrow is Thursday, and unfortunately, I have a medical procedure in the morning. I have to go to the hospitals at 8 o'clock, and I cannot, there's no way to change it. So what I'm going to do is, because I will not be here tomorrow, I'm going to do the following. I'm going to record the following: exam 1 and exam 2. I will record a review for them. So I will go over exam 1, exam 2 with you, and I will record them, and I will put them on Brightspace. So instead of just saying them to you in class, I will put them on Brightspace. So that's only for Thursday. Okay, so I'm gonna go over exam 1, basically to refresh your memory, and I will record it, and I will put it, and I will do the same for exam 2. Okay, Friday, it will be class as regular. Friday, our last day, of course. Friday, usually we have class as regular. I will review with you, and you will have a quiz. Now, why I'm giving you a quiz, why I am being mean, because I do want to make sure you get substitution. I want to make sure you guys can do the substitution correctly. So your quiz will basically focus on substitution. Did we do anything else? No, it's mainly substitution. All right, so you will have a regular quiz on Friday because I want to make sure you can do substitution and integration correctly. Now, the Friday class is a review. You basically can ask me any question you want from the review. I will be very glad to do it. And my idea was if you can focus on the problem that has to deal with substitute, the new material. So the problem that deal with new material were number 9, 32, 33, 34, 35. It's free fall. You guys can ask me anything. But if you want to focus on the new material, it means the one I did after exam 3. It's the number 9 in your review for the final, 32, 33, 34, 35. So you can go over those and ask me questions on Friday or anything else you want. Okay. So any questions? So tomorrow we will not have class, but please study. Please study. You don't have a lot of time. But I'm going to do that. So this evening, I hope I can do those. Friday, as usual, you ask any question you want, and then we will have a quiz. I want to make sure you know your substitution very well. Any questions before I let you go? Anybody? Okay, so if there is something you guys want me to talk about when I'm recording, just let me know. My idea is to go through those two. If you have anything else you want me to talk about, just let me know. Okay? Bye-bye for now. See you on Friday.
Have a good day.
Thanks. Bye-bye, guys.